Start recording. Okay. So everybody sees a bunch of slides?
Yes.
Awesome. And hi, good morning, everybody. Thanks for coming. Thanks for joining. My name is Magnus. I'm a PhD student at BIOS Lab at BERT. And I have the distinct pleasure of giving the final lecture in the Bayesian Machine Learning and Information Processing course, which is fantastically titled, What is Life? The Free Energy Principle and Active Inference. So first, a little bit about me and who I am. I've been a TA for this course, and some of you will have seen me sort of sporadically popping by the class forums, helping people debug their Julia setups and generally try to get things running. Otherwise, I've mainly done behind-the-scenes work, debugging notebooks, and generally trying to make sure that the class runs as smoothly as possible. Besides that, I come from a slightly different background to most of you guys. So I come out of cognitive and computational neuroscience rather than engineering. So that means I know stuff about brains. I know about how they work and what they do, how to model brains, how to process brain imaging data, and something about the kinds of computation that brains might be doing. My research is focused on that and the kind of things we're going to talk about today, which is applying that to study other kinds of systems. Right, so what are we going to talk about today? First of all, just for those of you who worry about these things, this is not going to be in your exam, so you can just lean back. Second, what I would like to try and do today is to give you a taste of the kinds of things that you can really do with the tools that you've learned in this class. And by the end of it, I hope that we can end up with some sort of an answer or an attempt at a simplified version of an answer to the questions in the title. Right. So what I would like to try and do today is introduce you to a couple of ideas and show you just how far we can push the tools you have already learned in this class. Because everything we've done so far, the vast majority of things, have been done in the service of processing data. And there's nothing wrong with that, right? We've learned how to update our beliefs when we get new data. We have looked at different kinds of distributions and how to work with them, how to model different kinds of data. We have had programming exercises where we have a data set and we need to do something to it. And that is probably going to be the vast majority of what people have to do for a job doing these kinds of things. You have a client, they will come, have some sort of data, you will do some processing, and that'll be the gig. But the tools that you have learned in this class are actually very, very powerful. There's a lot more you can do with them than just process data. Bayesian information processing can be a whole way of thinking. And I'd like to instill a little bit of a mind virus in you and hopefully get some of you on board with this way of thinking. Sort of as an aside, we're going to have a pretty traditional lecture format today, but I generally like to try and run a very interactive classroom. So I'm going to be asking you questions throughout, and I hope that you'll either type answers in the chat or just chime in with your opinions and ideas. Because the more interaction that we can get going, the easier it is for me to tailor what I do to what you need, and the more fun it is for me to do as well. So if everybody's game for that, then let's get into it. Okay, so this is the battle plan for all the things that I'd like to go over today. We'll split the class into two halves. In the first half, we're going to start out by talking about the premise for everything. And the idea here is that there are a bunch of ideas and intuitions that I would like to get into your head before we start to dive deeper on this. So there are a couple of ideas and a couple of starting points for how we're going to think about these things that are coming up. And I would like to just make sure that they're in everybody's mind before we proceed. Then we're going to talk about non-equilibrium steady states, NES, and biology. And that's because in the end, we are interested in talking about living systems, so like you and I. And that does necessitate doing a bit of biology. And from there, we're going to sort of try and loop back around and see how we can relate these things to base. Because after all, this is still a Bayesian information processing class. So we wanted to make sure that we can interpret these things as Bayesian. And once we've established that, we're going to take sort of a brief excursion and look at the concept of a Markov blanket, which is a really nice, it's not a particularly complicated construct, but it's a really nice piece of mindware to have available. Then we're going to have a little break, so like 15 minutes to stretch your legs, get a bit of coffee, maybe do a little bit of Q&A. And then we're going to look at applications of this line of thinking. So we're going to focus on first one of my all-time favorite ideas, which is the Bayesian brain hypothesis, which that's a part that I'm particularly looking forward to. Then we're going to look once again at the construct of the free energy that I know you've met before. And what we're going to try and do there is we're going to take the same ideas you've already seen, but we're going to tweak them a little bit. We're going to put a slightly different spin on it, a slightly different semantics, and something we're going to get like some really powerful and really cool things coming out. And finally, I put this goes to 11. And that's props for anybody who catches that reference. But that is if we have time towards the end. I'm just going to try and hit you with a flurry of ideas just to try and get your head reeling, get your mind spinning a little bit. Try to get you thinking about these things. So that is, if we have time, we're going to try and see how far we can actually push these tools. By the way, if at any point any of you have any questions, please feel free to interrupt me. Again, the more interactive we can make this, the better I think it is. So yeah, just feel free to interrupt me at any time. The other thing is, I'm not really going to be introducing anything new this time around. You've been bombarded with new information for the past several weeks. And that's not what I'm going to try and do. Everything that is here is all going to be stuff that you have seen before in one way, shape, or form or another. Again, we're just going to try and put different spin on it, a different interpretation, and see how far that can actually get us. Okay, so most of the stuff we're going to be talking about today is based on the work of this handsome gentleman on the right. This is Carl Friston, and I know you've met him before in some of Bert's lectures. There's a bunch of different pictures we can go with for him. I think this is a couple of years old. There's a lot of high-res, very superhero-esque, action-packed Quantum magazine front page covers, which are really good. But I kind of like this one. I think it makes him look a little bit goofy and a little bit approachable. And from experience, he's also a really nice guy. But don't be fooled. Like, this man is an absolute scientific titan, and along there with the top-sided most influential scientists of all time. This man is an absolute beast. So almost everything we're going to be talking about is based in one way or another on his work. All right, so everybody is clear on what we're going to do, the order we're going to do it, so roughly what the overall concept for the next couple of hours is going to be. Then we can start to get into it. And the way we're going to get into it is we're going to start with an example, or an observation, actually. And the observation is that most things in nature, if you leave them alone, they tend to dissipate. So you can think of a drop of ink in a body of water, for instance. Well, it's initially concentrated right where the ink hits the water. It'll quickly disperse and dissipate and sort of fill out this nice uniform distribution over the entire body. Clouds work much the same way. They'll form as these masses of vapor and then eventually fade out and dissipate. Or lightning bolts, which is a really dramatic example, where we're going to get this sort of snap self-organization into this really impressive, powerful structure, and then nothing. Sure, you can all think of like legions of other examples, like stars, for instance, which are also slowly dissipating. The point here being that most things in nature, if you just leave them alone, will settle into some sort of stable equilibrium with their environment, just if we do nothing. And I suspect this is not new to anybody, because, I mean, you've all studied physics in one way or another, but this is just the idea that everything will eventually settle into a stable equilibrium. Now, one of the systems we can think about that does this is a pendulum. And here you get to enjoy my my fantastic drawing skills in PowerPoint. Like, please don't judge me for the artistic expression. Judge me for the content. But anyway, like a pendulum, a very simple system that does this. If we have a pendulum and we leave it alone, it'll eventually settle into a stable equilibrium state where it's hanging straight down. So just like I've tried to depict here. It doesn't really matter what we do to the pendulum beforehand. We can push it, we can wiggle it, we can electrocute it. Eventually, unless we break it, it's going to end up in a stable equilibrium where it's pointing straight down. I know, like for the sake of argument, there's also a bit of an equilibrium that's pointing straight up, but just for the sake of argument, let's go with the pendulum hanging straight down. This is fine. It's an example of a system that settles into equilibrium. But there are other things we could want if we have a pendulum. We may want it to settle at an angle. We could want that. There are various reasons why we might want such a thing. But that's not as straightforward as just leaving it alone. So this is one of the occasions where I'd like to ask you guys a question. If we want the pendulum to settle at an angle, what would we have to do? I'm just going to briefly switch back to the Teams meeting so that I can actually see if you guys are typing. Apply a force, yeah. So this is not a trick question at all. This is pretty straightforward. So I see a thumbs up to apply a force. Any other suggestions? This is completely correct. Max suggests we hold it up. Yep, that also works. It doesn't put a structure in place to hold it. This is not a trick question. All of these are completely correct. What I want to get at is, if we want our pendulum to settle at an angle, we need to do something to it to keep it there. We need to apply an external force, or we need to put in some sort of structure to hold it, or have it float in water, or something similar. But there needs to be something from the outside that influences this pendulum. And if we have that, we can actually get the pendulum to settle at an angle. That means if we have an open system, we can get that is interacting with this environment, we can have that system settle at a non-equilibrium steady state. That is somewhere that is not equilibrium, somewhere where the pendulum is at an angle, somewhere that is away from sort of the stable thing, if we have an open system. So is everybody with me so far? I'll take the sounding silence as a yes. Okay, so why are we spending all this time on equilibria and pendulums and self-organization and all these funky things? Like that, this is supposed to be a class about bass, right? And the reason I'm spending all this time trying to go through these rather esoteric concepts is that I want to try and link this back to biology. Because for all of you, if you look straight down, you are going to see a biological system. Your view is going to be slightly different to mine because we have different biological systems. But as a rule, if you look straight down, you will see some sort of biological system. Now, as a system, you are made up out of stuff. And there's a lot of stuff that make up you. And all of this stuff can be in almost infinite number of configurations. But there's a very, very small subset of those that are consistent with you, being live and aware and here. And all those configurations are very, very far from equilibrium. You're not just an ideal gas that's diffused somewhere. You're a very particular configuration. You're an open system. You have to constantly interact with your environment to maintain this configuration. Right? And we can finesse that a little bit by saying that in order to maintain this configuration, in order to maintain this non-equilibrium steady state that is consistent with you, being here, being alive, there are a number of different variables that you need to keep under control, and to keep them within very tightly defined bounds. And these are things like body temperature. I'll try to indicate with a little thermometer. It's blood glucose levels. You need food to have sugar to power everything. It's blood pressure. It's too high or too low, your system is going to start to be in trouble. So there are various different variables that you need to keep within very tightly defined bounds to maintain the integrity of yourself as a system that occupies this stable non-equilibrium steady state that's consistent with you being alive and aware. So from the point of view of biology, this is nothing special. We've known this for years. This is just what we would call homeostasis. The idea that your body has a balance that needs to be maintained. And if everything is just right, then you're doing great. If it's off, not so much. So just to recap, so far we've established that we've observed that most systems in the world, they tend to just dissipate and settle into some sort of equilibrium. Also established that if we have open systems, we can get them to settle away from equilibrium. And then we've noticed that all of the biological systems that we know of are open systems. And the stuff that make up these systems occupies a configuration space that is very narrow and very, very far from equilibrium. It's far from random. And then we finesse this notion a little bit by saying that in order to maintain this non-equilibrium steady state, that is, to stay alive, there are a number of sort of very vital variables that we need to keep within very tightly defined bounds. So I'm going a little bit fast here, but is everybody with me so far? See Mike and Cone and Stefan are all chiming in with resounding yeses, and Can. Perfect. If we made it this far, then we're about through the bigger hurdles. All right. So again, why are we spending all of this time on biology and non-equilibrium steady states and homeostasis and all these, again, very esoteric concepts? Well, why am I spending time on this? Because it's a class about Bayesian information processing. And I'm doing this because I want us to get back to Bayes. Right, we're about to drop some Bayes up in here. And the way we're going to get there is through an example. So let's roll with the body temperature example from the last slide. Like, we all know body temperature is supposed to be at 37 degrees Celsius. That's how people function the best. So we're going to run a little bit of a thought experiment. Because I'm going to switch back to the chat again. And then I'm going to ask you, whoops, what do you think would happen to a person if we raised her body temperature to 50 degrees? Again, this is not a trick question at all. I'm going to put on my camera here because it's a bit easier. You would die. Yeah, you would be pretty dead. And these are not trick questions. Processes will fail. Yeah, like various different biological processes are going to start to break down. And most likely, yeah, as Cohen says, you're going to be pretty dead. It's not going to be a good time. All right, let's keep going a bit. So what do you think would happen to a person if their body temperature was at 40 degrees instead? And this is not a trick question. I'm just going to wait for a few answers. You sweat or get sick? Yeah. That's, you would absolutely would. Wear more in winter, get a headache, you die slowly. Like the last one, you die very slowly. Hyperpyrexia, you feel very feverish. Yeah, we're getting somewhere. Like, we're all converging at this idea that you're not going to be doing too hot. You're going to have like quite a bit of a fever. It's not going to be particularly good, right? You're not necessarily dead, though. Most of us have had a fever at one point or another, and it's not a comfortable experience. But we're still here. Let's try and keep going. I hope by now you're starting to see where I'm going with this. What would happen to the same person if we put her body temperature at 38 degrees now? So again, I'm just going to wait a bit for a few answers to take in. If you want, you're also like feel free to unmute yourself and just say things out loud. You function normally. Yeah, like again, I'm not playing any tricks here. If you're at 38 degrees, not much change since there are normal people have temperature at 38 for their whole life. Yeah. I mean, you're getting at the right thing here. 38 degrees doesn't really mean a lot. Like, some people might have a slight fever, maybe a little bit. Might not be a best day, but you know, it's not that bad. For most people, it's even normal, pretty all right. So what happens if we keep going? Now we say, let's put your body temperature at 37.1 degrees. Oh, shit. Normal. Absolutely. Not much. No, like really, nothing is really going to happen if you're 37.1. That's like well within the bounds of normal. That's exactly what I wanted to get at. If you're at 37.1 degrees, you're probably fine. You're probably fine. 37.1 is well within the bounds of normal, even though it's not 37 bang on. What I want to get at here is that even something that we know the sort of set point value of, like body temperature, we have a little bit of wiggle room. We have a little bit of give and take on either side. And we can still stay within the bounds of normal. But a number with a bit of wiggle room, if we know what that is by now, that's distribution, right? Sorry. Like, if I look at body temperature, there's a distribution centered around 37 that's consistent with completely normal functioning. Like, there are various reasons why you might be hotter or colder in certain parts of your body. Close to the skin, for instance, everything's going to be a little bit colder than deep in your core next to the heart. The blood flowing back from the veins is going to be colder than that flowing out from your core. You might enter into a sauna and you might heat yourself up. You might go outside in the cold or eat a large quantity of ice cream or something. But what I want to get at is there's a distribution over these particular variables that we need to control to maintain homeostasis, such as body temperature. We can write out. We go up here a prior and a target prior in parentheses for reasons that become clear a little later. Okay, so now we have a prior distribution, but we've also established that in order for things to settle away from equilibrium, there need to be open systems. Right? So we need to have some sort of way of accounting for what all these variables look like after we've interacted with the environment. That is, once we get some stuff that's coming in, we need to update our model, we need to update all our variables, and we need to get a posterior. Right? This is also fine. This is all stuff that you know. Now, the trick here is that we can view the task of any living system as that of staying alive. That is, it needs to maintain its non-equilibrium steady state. And it does so by lining up the posteriors for all the variables with some set of target priors that are consistent with the particular non-equilibrium steady state that it needs to occupy. So for you, for instance, that means keeping your body temperature in line, even when you are perturbed by stuff from the outside world. But if we look at this a little more, like the task of lining up two distributions, task of lining up a prior with a posterior, that is one of the things that you've learned how to do in this class. Like, this is an inference problem. This is a Bayesian inference problem. But more specifically, it's going to be a variational inference problem. And these are the kinds of things that you have already learned how to do. Right? You have a bunch of methods that you've learned for how to do these types of problems. That means we can take a lot of the tools that you guys have worked with, and we can now start to apply them to model living systems and systems that are trying to stay alive. To recap, like the whole line of reasoning goes, most systems, if we leave them alone, will tend to dissipate. Some systems, such as biological systems, do not do this. They exist as some stable state away from equilibrium. They do so by controlling a bunch of internal variables, such as body temperature and glucose and blood pressure and all these things. And in order to stay alive, what they are engaged in doing can be cast as a Bayesian inference problem of lining up all of their internal variables after they've interacted with the world with some set of target priors. This was a pretty big jump. Is everybody still with me? Because this is sort of the crux of why we can do a lot of the things that are going to follow. All right. Yeah, and I'm going to take the resounding silence to mean that you're all still with me. This is sort of the core idea that I want to present to you today, that we can model living systems using Bayesian inference in this way. And I've been talking for almost 45 minutes now. So we're going to go through one last concept, and then we're going to do a bit of a break, maybe a little bit of Q&A, and then we're going to get back to the second half of the talk. So the final thing that I want to introduce as a bit of mindware to get you guys going is the idea of a Markov blanket. So you guys will have seen this figure before. This is a factor graph that Bird also used for the intelligent agent. But we're going to use it in a slightly different way here. So what this thing really depicts is a factorized model. That is, we have a bunch of dependency relations between different variables. And you'll notice that given everything on the dotted line, all the internal variables, all the S's, are independent of everything outside of the dotted lines, so the giant R. And that means that we can delineate a system by saying, if we can wrap a blanket around it, this Markov blanket, it is now independent of the world around it. So to pull that a little bit more down to earth, in your case, for instance, we might be able to draw a Markov blanket at the skin. As we're saying, given everything that happens right at the border of your skin, all of the internal stuff, everything that is inside of your body, is independent of everything on the outside, given that we know everything that happens at the skin. So thinking about what constitutes a thing or an object or a system in this way gives us, again, a tool within the Bayesian framework to delineate between things. So some things will occupy non-equilibrium steady states. It means we can draw Markov blankets around them, and they'll be doing some sort of inference in order to maintain internal variables. Other things like gases and whatnot will just settle into equilibrium, and they don't have all these nice properties that we want out of living things. So yeah, the idea here is that we can separate objects based on dependency relations. And being able to separate an object from everything else is really handy when we want to talk about things. Another way of writing this, which is handy sometimes, is that we partition everything in the world into 4 groups of variables related to a system. And I've drawn them here as sort of a Bayesian network type thing. But the thing is, we can think of, on the rightmost side, we have this mu that denotes the internal states of an object. So in your case, that would be everything inside of your skin. On the other hand, on the left-hand side, we have an eta, which denotes the external states of an object. And this is reversed because eta looks almost like a mu flipped upside down. And that is everything that is not a part of it, everything that is on the other side of your Markov blanket, everything else in the world. And then we have the blanket. Blanket is these 2 guys here in the middle. And we're going to partition all of the variables that make up a Markov blanket into 2 groups. We're going to have what we're going to call sensory states, which are all your observation channels, all your likelihoods. In your case, for instance, it might be your eyes and your ears and all the little touch receptors that are scattered all over. Then we have active states. Active states are things that you can use to influence the world around you. That's why we have this circular graph thing going. The external states will influence your sensory state. That is, light from the outside world is going to be hitting your retina. That's going to influence your internal variables, so all of the stuff that goes on inside your blanket, such as all the neural activity that translates light on the retina to things that make sense to us. And then you have the option of influencing the outside world through action. These would be things like activating your muscles or excreting pheromones or different things that we can do. Like right now, I am part of your external world, and I am directly influencing the sensory states by putting little vibrations in the air that you pass as me talking. And if you wanted to influence that, you can say grab the volume control on your computer and you can turn me up or down. The point I want to get at here is that there are actually, if you think about it, two ways for an organism to bring its internal variables in line with a set of priors. Either we get new data coming in and we update the model. That's fine. That means if you believe that you should be at 37 degrees and you go outside and it's cold, you will register a drop in temperature. That means now you update your model and you go, oh, damn, I'm now cold. But you can also go and you can intervene directly in the data generating process. That is, you can put on a jacket. You can do so to change the external world such that the observations that you get, that is whatever is impressed upon your sensorium, is different in order to influence your internal variables to keep them in line with your priors. Again, it was a bit abstract, but it means that we can start to think about agents and active systems and biological systems that do things, again, in this sort of Bayesian way, by partitioning the world into sets of states and then thinking about the kinds of things that happen on that graph. And I think that is all I have for the first half. I'm going to stop sharing my screen and put this back on. And then I suggest about a 15-minute break. I'll be here to sort of talk about the different things that are going on if you have questions. Otherwise, I suggest you grab yourself a cup of coffee and I'll see you back here at 1:45, so 11:45. Does that work for everybody? All right, cool. Then, yeah, I'll see you in 12 minutes.
Are you going to keep the recording on, Magnus?
We can also do it in 2 parts. I was going to keep it on in case there were some discussions happening.
All right.
But otherwise, we can just do this.